Hi everyone, it's great pleasure to have this opportunity to present our work, DisCo-CLIP, a distributed contrastive loss for memory efficient clip training. This is joint work between Yi Haochen, 线标旗, Jianan Wang, and Lei Zhang. I am 线标旗. We are from International Digital Economic Academy. IDEA. The motto of IDEA is the world needs a few good ideas. Okay. First, let me highlight the contributions of this paper. In this paper, we proposed DisCo-CLIP, a free launch improvement to the original clip. DisCo-CLIP can reduce the GPU memory cost and also reduce the computational cost. And mathematically distributed contrastive loss is equivalent to the original contrastive loss. Is not approximate to the contrastive loss, is exactly the same result as contrastive loss. And from our experiments, we also found that large batch size can further improve the performance of contrastive learning. So this is the original clip, and this is the DisCo-CLIP. This is I1, I2, and I capital N, and this is T1, T2, T capital N. And this is a feature in the first GPU, in the second GPU, and we called it IA. IA means all image features, and TA means all text features. Okay, our target is to compute the partial L, partial I1, and partial T1 in the first GPU. And then in the second GPU, our target is to compute partial L, partial I2, and partial L, partial T2. Yes, to compute the gradients, we need to actually in contrastive learning, we need to compute the full similarity matrix. Actually, this similarity matrix is very, very large, and for each GPU, you need to do the same thing to compute the similarity matrix between IA and the TA. So it will cost a lot of memory actually in each GPU, and it will also waste a lot of competition. Okay, this is the DisCo-CLIP. Actually, you can see that in DisCo-CLIP, we don't need to compute the full similarity matrix. We only need to compute a slice of the similarity matrix. So this is I1, and this is TA. Okay, you can also the same way T1 and IA. Okay, so you can see that in our solution, you can save a lot of computational costs, and you also save a lot of memories. So our motivation is very clear. We want to train clip more efficiently. We want to train clip with large batch size. We want to train clip with limited GPU resources. So first let us review the contrastive loss in CLIP. CLIP is contrastive language and image pre-trained model. The original CLIP contrastive loss is LD equals to L1 IATA, L2 TA IA. This is image to text loss, and this is text to image loss. And IA and TA, as I talked about before, denotes all image and text features. And for each GPU, you will calculate the full IA times TA similarity matrix for the contrastive loss computation. It will waste a lot of computation. So what we can do to see how we improve the CLIP, we can see the gradient flow. So let me define some concept. This is IA equals to IN and IN inverse, TA equals to TN and TN inverse. IN means the feature in the current GPU, in the nth GPU, and this is IN inverse. This is the rest features in other GPUs. Okay, so to calculate LD, we can the LD can be decomposed as below. Yes, LD equals to L1 T IN TA I inverse TA TN IA and TN T inverse IA. Okay, so what we need to do is to compute the partial LD, partial IN. So partial LD and partial IN. So we need to compute the gradient with respect to IN, and actually we can find this as this term is not related to the partial IN. So this 4 term can be transformed into these 3 terms. Yes, and also similarly for the text feature, we can also do the same thing. Let's see this. This is INTA and TNIA is only a slice of the 4 matrix. Yes, 4 similarity matrix. Yes. So this is this is will be very small, and this is also be very small, and I means the GPU memory also means the computational cost. And for this part, actually it will be large, but it will not be calculated in the current GPU, the nth GPU. It will be calculated in the others capital N-1 GPUs. So what we need to do here is we can use touch dot or reduce to make a communication between GPUs and to collect all gradient with respect. So for this part we calculate it in the current GPU, and for this part we use touch dot or reduce to collect from other GPUs. So this is the main idea of our paper, and this is a pseudocode of DisCo-CLIP. Yes, and this is IATA and this is INTN, and this is the compute the similarity between IN, TA, TNIA. Okay, so after that we can compute the loss and also do a backward. After here we need to use dot or reduce to collect the gradients. After that we can continue the backward. So this is the DisCo-CLIP. Let's see the experiments. For the original clip, if you use a batch size larger than 65,000, it will be out of memory. But for our DisCo-CLIP, we can use very large batch size, like 200,000, and we can still train it. Yes. So what's the benefit of using large batch size? We find that using large batch size can further improve the performance. That's why DisCo-CLIP can get better performance. Okay. So let me make a conclusion. DisCo-CLIP is mathematically equivalent to the original contrastive loss, and it can largely reduce the GPU memory cost. It can also reduce the computational cost, and the most important is the free launch. Okay, thank you very much. Thanks for your attention.